Thank you. So welcome everyone to the afternoon session, last session of the workshop. So now we're going to hear from Eduardo Novais from University of ABC, spectrum of entanglement as a dimensional reduction tool for studying topological insulators. Edu.
Thank you very much. Thank you very much for the organizers for inviting me to this conference. It's wonderful to be here, and especially because it's Eduardo's birthday. And, oops. Oh, I'm without it, sorry. And it's special because it's Eduardo's birthday. It's very nice to be here. And this work I did with my undergrad student, Marcela, and she's been working in a different topic, but very related to what I'm going to talk about. She's working with the Hofstadter bands. And although I'm the Federal University of ABC, it's not because we are kindergarten school. It's because the ABC is because there are 3 cities that are touching São Paulo, Santo André, São Bernardo, and São Caetano. And so this is the university, the Federal University that serves these 3 cities. Okay. And so, well, when I was in Vancouver a couple of years ago, they asked me, what about this name? So let me talk a little bit in the spirit of this conference about my history. So I was a student at Campinas under the supervision of Guilherme Cabrera, which was my PhD advisor. He was my master thesis advisor too. And I was working with the BET ansatz for a long, long time. And a certain afternoon, Cabrera told me, you know what? BET ansatz is like a very dark forest with a really bad wolf inside. Sometimes you send a student and it never comes out. So and then I realized I don't want to do this for the rest of my life, you know. And so I decided to take some time for an exchange program. And Cabrera sent me to Antonio Castroneto in California. And I went there, and I started learning a lot of many-body physics from Antonio and quantum field theory from Antonio. And he gave me a problem, you know. He gave me gave me a paper from Kivelson and Oron Zakar about the Kondo chain using bosonization, and he said, you know what, you're going to work in that. Okay, so I started working that. And after 7 months, I barely scratched the basics of bosonization. And I had to come back to Brazil. And Antonio told me, you know what? You have to go back to Brazil, to Campinas. So you have to talk with a guy that was just hired there, Eduardo Miranda. He was just hired, and he's the only person that's going to be able to help you with that problem. And so I went back and started working with Eduardo for the rest of my PhD thesis, right? And during many, many afternoons, on Saturdays afternoons, I went to his office, and we would talk about physics in the Friday afternoon. And it was wonderful, and I learned a lot from him during that time. So here, after some time, right? So I had my thesis, strong correlated systems, studying one-dimensional systems, the one-dimensional Kondo lattice with bosonization, and the Heisenberg chain with BET ansatz, a study about that subject. And here you see, Guilherme Cabrera was the advisor, and Eduardo Miranda, and I became actually the first student that Eduardo was an advisor in Campinas, right, in 2001. So, and in the in the beginning of my thesis, you always put those sentences, right, in front of it. And this one is from a book from Stefan Gold, Wonderful Life, The Chance in Evolution and Natural History. And it says in this sentence, right, it's in Portuguese because I had the book in Portuguese, that, you know, there's an asymmetry when you are a grad student and you are in science. Everything that you do right is because you had your advisor. And everything that you do wrong, it's your responsibility. And we all accept that because one day you're going to be on the other side. So, Eduardo, don't worry. Everything that is wrong here is my fault. All right. So let me start explaining where I started. When I came back to Brazil after many, many years in the US, I went to a wonderful school that we have in quantum information in Paraty, which is a neighbor a city in the seashore of Rio de Janeiro. It's a historical city. And there I met George Matzes, which is a professor here at the FT. And he works in field theories and in curved spacetimes. And he talked about the room effect. And after his talk, we went to lunch together, and he explained to me. But I wasn't really paying attention, you know. I was saying, well, that's fine, that's interesting. But I couldn't see connections to the things that I was doing. A couple of years later, one of his students, André Landulfo, was hired at Federal University of ABC. And we share an office. And he explained to me again the room effect. And I said, wow, this is really, really cool. It's very interesting. But I don't see the connections with the thing that I did. Eventually, Manaus and other guys published a wonderful paper about this in Nature Physics. Over effect. I said, well, you know what? I should pay attention to this stuff. You know, I have someone here just beside me that knows the Unruh effect, and so probably I should learn it. And so let me explain the Unruh effect in a nutshell. And the idea is that, well, when you have space-time, there are only two possible ways that you can foliate space-time. You can have the normal frame of reference that we are used to, when you have, for example, the ground state of your boson field or your fermionic field is there. Or you can have an accelerated frame of reference where you create these two wedges or different sides of your system or of your space-time that are not connected with each other, and they are related by time reversal symmetry. And now you start with your bosonic field, which is at ground state, for example, and it's at 0 temperature. And when you go to the accelerated frame, in the accelerated frame, you see a finite temperature, some excitation. So it's an effect of the accelerated frame. And Unruh proposed that because he was trying to understand Hawking radiation. So this is a toy model for Hawking radiation in a certain sense, and to understand black hole radiation. But the Unruh effect is very general, works for non-interacting systems, for interacting systems, for fermionic systems, for bosonic systems, and have been studied for 50 years. And this is kind of interesting because what you have is these two wedges which are related by time reversal. So here you have an observable that will move at constant acceleration, and this is this curve that he does, and it's related to by time reversal with the left wedge with another observable at constant acceleration. And why do you have the wedge, the disconnected parts of your space-time? Because you're moving so fast, you're accelerating so fast that some of the bosonic modes of one side cannot propagate it and give information to the other side. So you kind of disconnect the two sides. And how they explore this? They put a thermometer, which is a two-level system interacting with your bosonic field or fermionic field, and they see the level, how the population of these levels change with the acceleration. So keep in mind, from everything that I'm going to talk about in condensed matter, that this is exactly the starting point, and try to see the connections that I'm going to try to address and show that these two problems do have. No, I don't think so. Maybe, but I don't know. So I went down this rabbit hole, and let's start with our topological systems. And we know a lot about topological systems in this band theory slide, right? We have topological invariants, and it's a well-defined and clear picture of what means to be topological. You have your band theory, you calculate your topological invariant, and that's it. Okay. So what is the key lesson that we can learn from this? We can learn that in quantum mechanics, we always talk about eigenvalues and eigenvectors. And in the original, for 50 years, our paradigm was that you have eigenvalues, then you define order parameters, symmetries, and you get your free energy. This symmetry should be here, but I guess that was squeezed by the projector. And then you define the free energy, and you calculated phase transitions, as Musi was talking about. So this is the paradigm for 50 years. But the key lesson now is that on topological systems, the eigenvectors determine the physics, not the eigenvalues. So the information that we're looking for, the properties, are encoded in the eigenvectors and not in the eigenvalues, as we start in the usual Landau paradigm. So the idea is that, okay, isn't the eigenvectors, so how does this change when you introduce disorder or you introduce interactions? Can you still well define topology in these systems? And the idea, in my point of view, is that yes, because information is the eigenvectors, so it's in the full many-body wave function somehow, so you need to try to explore the physics of the wave function of your system. So the key idea here is to try to describe the wave functions, the ground state that you're looking at, in a very clever way. And most of all, try to leverage as much as we can from 1D physics, because we know how to deal with interactions in 1D. And it's very hard to go to 2D. 3D, we also know quite a lot, but 2D is kind of hard. So I'm going to talk about two-dimensional systems, which are topological, and try to look for some form of 1D hidden structure inside these 2D topological systems. All right. So there were routes that were taken in this direction before. So we have people that have been working on this subject here. For example, Claudio was talking about topological classifications, classification of topological phases using 1D quantum wires. And you also have this wonderful paper from Kane, where you introduce your Luttinger liquids in one-dimensional Luttinger liquids and introduce hopping and see what is the topological phases that comes out of that. So in this sense, it's not exactly new, but it is a different perspective, what I'm going to talk about. And you can write, or you can say that the name of this seminar should have been Haldane's Tale, because actually I'm going to talk about spectrum of entanglement and also the Haldane model and many variants of that. So the Kane and Mele problem, and I'll also introduce local levels, which are the probes of my wave function, just like in the problem that I was discussing about general relativity or accelerated systems. So, but before that, let me talk about hard wall and what we teach our students in quantum mechanics, right? One thing that you do is that when you introduce a hard wall in your problem, you have to consider the boundary conditions. And when you consider the boundary conditions, right, if you are in a very simple setting like that, you have a bulk solution that has to die on the boundary, which is a wave. And you also have localized states, right? So what happens in the transverse direction will depend on the system, but you expect that the direction towards the bulk, you have an exponential decay of your state. So that's what we teach our students in Physics 101. And here is some example of that, right? So edge states in graphene-like systems, you see that you can have zigzag edge, or you can have the armchair edge, and the physics is quite different between the two. Right? So the zigzag edge has boundary states with 0 energy, and the armchair edge has boundary states away from the Fermi level, right? And the physics behind that is quite simple for this tight binding kind of problem. For 1D, for this kind of tight binding model, you just need to count the number of sublattice, blue sublattice sites that you have more than red sublattice sites, and you're going to see how many 0 modes you have. So this is something that you can prove. And that's why your armchair has this flat 0 mode band here, and your armchair doesn't have it, right? So a more sophisticated and well-established results about boundary conditions can be seen in this Wheaton set of lectures in topological phases of matter, which are quite interesting, but very hard to read as usual, but very nice to know that there are someone thinking about this in terms of the Dirac equation, right? So what we learned from that we actually have, in very general settings, you have a reference state, you have bulk states, and you also have boundary states. So in a second quantized language, you expect to have boundary states which are created, and you also have bulk states. With or without interactions, every time that you have some quasi-particle interpretation of your system, in your system, you can use that, right? So let me now start with the entanglement entropy. What is entanglement entropy? So Haldane was looking at the quantum Hall state, and he put this following problem. You have a monopole inside a sphere when you have your system which is creating the magnetic field, and now you compute the wave function. And then you trace half your wave function, trace half of the system here. So what they found is that when you do that, you do a Schmidt decomposition of your state, and the Schmidt coefficients that appear, the logarithm of them, will actually reproduce the low energy excitations of the boundary states, of a real boundary, of an open boundary Hall bar in top of your experimental table, right? So this was numerically verified. He has the conformal towers, and he put that forward in 2008. And he called this spectral of entanglement, because it's actually how the two sides of your semisphere were relating to each other. You're tying up together the two boundary states, boundary conditions, the one hemisphere and the other hemisphere, right? So, and it gives extra information than the entanglement entropy, which is a measurement that you can do, you can calculate it, and see if your system is topological or not, even without the boundary. But he was arguing that this has extra information. So what do we have? Well, you have an arbitrary path in your system, and you introduce a hard wall boundary. And then you have your Schmidt decomposition. And what happens if you are looking at an observable exactly at one of the edges, in one side of your boundary that you introduce? It's an imaginary boundary. You're just trying to describe the wave function using a different set of bases, right? Because you have the right bases in the one side and the left full bases in the other side, and you want to know how to calculate this operator O here. So the idea is that, well, it's actually independent of what the right wave functions are and the bulk wave functions in the left. The expectation values of these operators will only depend of the wave functions or the states that are at the boundary. And the reason is quite simple, right? Remember that I said that bulk states will have to die at the boundary. Wave excitations will have to die in the boundary. So the contribution to the expectation value of O there will be 0. So if we remember that picture for the left states, right? To have a full set of states on your left side of your system, you don't have to consider the bulk states if you're looking at the probe, at the operator O that is at the boundary. And so if you start with a few set of states, you only have to worry about the boundary states. And your expectation value in your spectral entanglement are actually boundary Hamiltonian, the boundary operators that will have the energy spectrum that you need to produce your Schmidt coefficients. Yeah. It's just that I need some way to label the states. And that I'm saying, well, there's some quasi-momental or a certain number there, or a certain way to label the boundary states. It can be a momentum or it can be a position, but something that I can use just to label the state and say, okay, if I can construct in the second quantized image just by applying a construction operator into a reference state, right? And then I'll have that. It doesn't have to be a free system. Yeah. This is not really important. It's just that I need a certain set of wave functions in the boundary, and I need to know that what will be the Schmidt coefficient to label, to compete, to match with the other side to construct the original wave function. So the idea is that you have a wave function in the entire system, but I'm instead of having a base for the entire system, I only using a base for the left, a base for the right, and then I'll have to match at the boundary the wave functions. And so this is the Schmidt coefficients. So the Schmidt coefficients are the things that will give this Hamiltonian, given this, the eigenvalues of this operator. And what I'm saying is that only the boundary states are really important for things that you're calculating at this fictitious boundary. And so, yeah. They are simply what?
The boundary state and the both state, they have a simple direct product.
Yeah,
why are they not entangled in any way?
They are not entangled in any way. The idea is the boundary states are very, they exist in the boundary. They have an expectation value different in the boundary. And you have the bulk states or states that are propagating. And they form a basis for all the possible wave functions that you can construct in one side of the partition, on the left partition. And then you have the right partition. And the coefficients that you are trying to calculate is how to match these two bases to create the original wave function, which is defined in the entire space.
So this is just by definition, you want to write the L this way.
I just want to write I just want to write my full wave function as the product of a basis that is defined only on one side and a basis that is defined only on the other side.
And with the help of these boundary states.
Mm-hmm. Wait, it doesn't exist. It's just an imaginary thought. Just like in Haldane's calculation.
No, I understand. But in this imagination, you're going to construct these two sides but with the help of this imaginary boundary state, which you by definition is only the direct product with the other side.
You calculate them, right? You can put a boundary, a real boundary, and calculate what are the wave functions in a real boundary. And then you're going to use the semi-infinite system to define what are these operators.
Right, but if I do that simple calculation with a real boundary, my boundary state will not be just a direct product with the both state, right? They will be entangled. There will be a lot of superposition.
Only if you, that's why I'm saying I need to have some idea of a quasi-particle picture. So I will have a quasi-particle state in the boundary, which is this, will to have a wave function will decay inside the bulk, and I will have wave states that will propagate it in the bulk, right? So if I do have that, I'll have my bulk state, my basis to construct any other wave function using this basis.
Right. I guess what I'm a little bit confused is this formula you write down always possible? Is it exact statement?
It's not an exact statement.
Or was it like a construction that you wanted to try this and see whether you can get some information of the whole system?
The idea, the problem, I understand your point. And it was always confused for me because it actually works. And that's what I'm going to try to talk about.
All right, thank you.
Because, so this is an important work that was done by Ludwig, in my opinion, very important. Oh, it's really bad here. Which, if you have your wave function, your full wave function, if you have your full wave function in a Hall bar, for example, and you break your Hall bar, then you create your edge states. So these are these breaking that I was talking about, these imaginary cuts. And they were able to show that you can always write the full wave function as a product of an exponential of minus beta over 2, a right boundary operator, and a left boundary Hamiltonian operator. So these operators are only defined at the boundary, and they are these exactly spectrum of the boundary states of a real bar that has a real edge. And so the physical picture is that they have an exactly state which is conformal invariant, which are called a Shibashi state. They are just the maximally entangled states between left and right. And then you have a projector. And this projector has this very intuitive form of a Boltzmann weight. And this was called by Cardy as extrapolation length, this beta. And they show here that it's related to the bulk gap. So what you have two, in this case, they have two Luttinger liquids here, defined at the two boundaries. And here you have the extrapolation length, which is proportional to the inverse of the bulk gap. And because of that, you can define an entanglement temperature. And then you see that what you're doing is that when you write your system in this way, you can trace the right part of it, for example, and have a theory only on the left. But it's a theory only on the left at a finite fictitious temperature, which is this temperature of entanglement. That is how you match the two sides to construct your original wave function. All right. So other people work on that. So Fradkin also work on that in ladder systems. And here you have a very general argument for Sentil that do exactly the same. And actually, this Sentil work use the Lorentz boost exactly like the Unruh effect does to show what you're doing. So there is a general argument that I can also do that says that why do you have this Boltzmann weight form? Do you need to have them? So there is oh, this is so bad, I'm so sorry. There is a general argument that, okay, entanglement wave functions in general, when you trace out part of it, will not have a Boltzmann form. And for a long time, people were trying to calculate the foundations of quantum mechanics, the foundations of statistical mechanics. They were trying to get the Boltzmann form for the weights. But then Popescu, in this work in 2007, and I remember he was discussing this in a seminar, he was saying, oh, we made a really jump in our understanding when we realized we didn't have to prove exactly the Boltzmann form. Just that every time that you do this reduction of the density matrix to a partial matrix, to a reduced density matrix, you have to be exponentially close for what you get with the Boltzmann weights. And that's what they prove. When you have a highly entangled state, it's very likely, so with almost 100% probability, if the system goes, your environment goes to infinity, that you will end up with something that is always exponentially close in any operator that you try to calculate, expectation value of any operator to calculate from the Boltzmann weights. Okay, so can I prove that? No, I cannot prove that. But I can tell you that for topological systems, it seems that it really works. And because of that, if you have an operator in a boundary, I can try to calculate it, the expectation value, the evolution of this operator in time, or I can also, but at a fixed, or I can also look at thermodynamical quantities when I introduce interactions in my system, but not looking at the entire wave function, but looking at this one-dimensional boundary that I just introduced into the system. So these are the two ideas that I'm going to try to follow here, and I'll try to explain with two examples, right? So let me skip the Lieb-Hobson bound. Introduce that you have introduced a fictitious boundary. You have an original wave function that you're trying to explore, but only the boundary states will be important to expectation value of operators that are defined at the boundary. And and the boundary comes at a cost. And the cost is to work at this fictitious finite temperature. All right, so let me go to Haldane's model. And people here know quite a lot of Haldane's model. I don't have to explain much. It's the hexagonal lattice with second neighborhoods, and you have your Kairos hoppings there. And when you do that and try to calculate this entanglement entropy, what we do is that, okay, let me choose a certain path. A path here through sublattice white. Why I do that? Because now this will have a Luttinger liquid edge in the theory that will be a boundary, because this will be exactly this zigzag edge that I'll have there. So now I'm going to introduce an extra level there. I'll introduce, for example, a resonant level model there in a certain position. And I'm adding this to the Hamiltonian and try to calculate the dynamic of this resonant level. So one thing that you can do when you have resonant level models, right, is calculated this quantity that is defined in many, many papers, in Paco Guinea's paper, and also the Leggett review, which is, okay, you put a charge there on this resonant level and see how long it takes to get out. And so this quantity, if you're in a no-interacting system, depends only on the hybridization between the local level and your band, and the cutoff of your theory, right, the bandwidth. There's no dependence, for no-interacting system, there's no dependence on the temperature. You can put temperature there, and there's no dependence on the temperature. But now, if you introduce interactions, the interactions relevant for this resonant level, because it's at the boundary, can be only forward scattering, because you have chiral symmetry. So even if I start with the bulk model, which will have some Coulomb interactions between my electrons there, which are controlled by the band gap, I could also introduce forward scattering here, and we'll have a Luttinger liquid theory, and we'll try to look at what is the Luttinger liquid theory. And now I do have a dependence on the temperature of entanglement with the temperature of the system, of this fictitious temperature that I'm working, and also in the Luttinger parameter, which is a measurement of the interactions in the material, in the bulk. All right, so another model that we can look at is the Kane and Mele model. And now I'm going to introduce a two-level system here with a Hubbard U. And when you do that in the large U limit, you end up with some Kondo coupling. And when you do your Kondo coupling, now you have a Kondo coupling with a Luttinger interacting with a Kondo model interacting with a Luttinger liquid. You can have this G parameter here and calculate what is the thermodynamics of this system. And when you do that, you define your scaling equations in the standard way, and you can define a Kondo temperature, and now you have a competing of two scales, the Kondo temperature and the temperature of entanglement. When you do that, there's two limits. The first limit is when the Kondo temperature is much larger than the temperature of entanglement. And when you do that, in the large JK limit, when you go to strong coupling, you form a singlet here, and this introduces edge states around it. So, but the Kondo cloud is not something well defined. And so it's hard to imagine that you're going to have these edge states moving around inside your sample. But you can see that the entanglement, the characteristic length scale that comes with the bulk gap will introduce forcibly a region where you're going to have your bound state or your edge states inside the sample. So an old picture that Kyle told us in the beginning of the week is that you can have this impurity in your systems and they can melt your topological system. But then he said in his seminar, right, that, well, they have too few impurities there to actually melt the system, and it seems that this doesn't explain the behavior that they see. But here I'm saying, well, you know what? There are very few impurities, but the Kondo cloud can be very large. So you can actually melt the topological system, even having not a large number of impurities inside of it. Melting means that you are kind of mixing one edge state with the other edge state. So, and what is the other limit? The other limit is when the temperature of entanglement is much smaller than the Kondo temperature. And then you can conformal boost because you're just working in a Luttinger liquid at finite temperature, and you have your propagator two-point function and the propagator for this theory, which depends on the temperature of entanglement, which depends on the gap, and also the Luttinger parameter, and you can create an effective interaction between your spins. So, okay, now I have two spins. I put two spins, two-level systems in different places. And I said I had an arbitrary line or separation between left and right. So which one should I choose? I can choose this path. I can choose this one, this one. It was a fictitious boundary, right? Well, yes. And I'm sorry that it's horrible, but the idea is that, okay, it's a fictitious boundary, and now I'm understanding what I'm doing. I'm actually choosing 1D channels that will propagate better inside this 2D system. 1D Luttinger liquids inside this system. And I have to sum over all fictitious paths. And when we do that, there are not too many of them because they are controlled by the bulk gap. I'm almost done. And they are controlled by the bulk gap. So what we are actually doing in the end of the day is creating a path to a kind of 2D bosonization. I'm saying if I have any pair of operators, places that I want to compute the correlation between them in the system, I can choose all possible paths between them that are one-dimensional, and they contain exactly the Coulomb interaction in the Luttinger parameter in these 1D systems, because they are protected by time reversal. So this is a very nice and clear path to 2D bosonization in these topological systems that do have a gap. If you do not have a gap, then you have log corrections, as you expected, because then you have a marginal Fermi liquid in the 2D system, right? And can we start thinking about Doniak phase diagram, as Eduardo told me once before, many, many years ago? Yes, we probably can start thinking about magnetism and heavy fermion physics in these systems in this way, right? When you're going to have 3 competing energy scales. The temperature of entanglement, which is related to the bulk gap, the Kondo temperature, and the temperature that comes from the effective coupling between your local spins. So, in conclusion, we have this ideal spectrum of entanglement that can be used to introduce interactions in your system in a very systematic and quite formal way, without many approximations. We also can discuss several probes, like the resonant level model or Kondo-like coupling. And finally, it seems to indicate there is a possible scheme for 2D bosonization, at least on these kind of systems, right? So now I finish saying that I came full circle, right? Because Antonio did his PhD thesis in bosonization in higher dimensions with Eduardo Fradkin, and Eduardo here worked with a lot of things in the Kondo lattice, and I hope that we can contribute in this direction again and looking at Kondo lattices inside these topological systems, right? And so thank you guys for all the knowledge that you gave me and Antonio gave me, and happy birthday, Eduardo. Thank you.
Questions? Many questions?
Could you relate what you just told us to the Unruh effect?
Oh, yeah. So what are the probes, right? The probes are these 2-dimensional systems. Then you tell me, what is the Unruh, what is the relation with the Unruh effect? So what they do is that they have space-time, and then you have your 2 wedges, right? The left and right wedge. And now you have your constant acceleration observables here. So this, I will put my 2-level systems on them, right? And this will be at a certain temperature. So the 1-dimensional systems that I'm talking about have a defined fixed temperature, right? So the way to imagine that is that my 1-dimensional system is actually a system that is going in this direction here at a constant acceleration speed, right? And so this is the relation with the Unruh effect. And why it comes this way? Because when you try to look at correlations and entanglement, you see that these hyperbola is actually maximally entangled with this other hyperbola on the other side. If you look at the other hyperbolas, they are not so much entangled. The entangle goes down as you go away from one another, right? So exactly the left. This is the left and right. Here's the boundary that I impose, which is the boundary that I'm just imposing, that is separating the two, and the entanglement between the left and right Luttinger liquids, right, is the temperature of entanglement is the Unruh temperature. Yeah.
If I understood correctly, I think you're describing systems that are gapped in the bulk.
They are gapped in the bulk.
And they might have Lorentz invariance at low energies at defect boundaries, or sometimes even conformal invariance.
Yes.
But do your notions generalize to other systems which don't have, some of these properties?
Well, the idea of having boundary states in the spectrum of entanglement is fine, right? You can always do that. The problem is, what is the effective theory for your Schmidt decomposition there? And what I'm saying is that for these systems, it's quite well established that Schmidt decomposition coefficients are related in low energies to the boundary state theory. And so this is a clear thing, and that's why it's simple to use here. But the idea of having the Schmidt decomposition and looking for ways to use it to explore the many-body physics, I think is quite general.
Okay, very nice talk. I was just thinking about this room effect stuff, because usually people associate it with some quantum field theory in the curved space-time, right?
Yes, that's right.
Do you have this notion as well? What is your curved space-time? Do you have
Well,
a metric? Do you have a metric?
Yeah, what is the curved space-time here, right? So the Unruh effect is actually in flat space-time, but you have the acceleration. But by the equivalence principle, this is equivalent to be in a constant gravitational field. Right? So that's why it's related to the Hawking radiation, right? So the idea of the curved space-time enters here as this constant gravitational force, which is related to the constant acceleration in the Unruh effect.
Do you just make it as decelerate, or what
I'm sorry?
I mean, do you just make it accelerate, or is
No,
there a curve?
The Unruh effect is at flat space-times. That's what I'm saying.
Yeah,
So
but
the Hawking problem is that in the curved space-time. But the two are related by the equivalence principle, right? When you cannot distinguish acceleration from a gravitational effect.
Yeah, quick one. So the result of Popescu, I think that this proximity to the thermal state, it was for, I think, volume law, right?
Yeah, it's just an argument. I'm not claiming that can be used exactly,
yeah,
but just...
But I wonder if then the conformal invariance, like, that can actually make it valid even for the ground states of the bulk, right? When you look at the entanglement Hamiltonian, maybe you'll have that form because of conformal invariance.
Maybe. I don't know. I don't know the answer. But the Popescu idea I always thought that was something that 50 years from now we're going to teach in statistical mechanics classes. And that's why I think it's connected here somehow.
Okay, thank you.
Thank you, guys.